to the computer. Okay, continuity. So when we say a function is continuous, we mean that it's not broken. We mean that you can draw it without lifting your pencil. So the informal definition of continuous is you can draw it without lifting your pencil. Wow. You can draw it without lifting your pencil. That's the informal definition of continuous. So if you look at a picture and you say, yep, I can draw that in one continuous line without lifting my pencil off the paper, then you're going to say, yeah, it's continuous. If you can't, then you're going to say it's discontinuous. It turns out that if we think about continuity in terms of the limits that we did last week, then there are three things that have to happen, okay? If you want the function to be continuous or not broken, then you need it to have no holes, you need it to have no breaks, and you need it to have no jumps, okay? So those are the three things that have to happen: no holes, no breaks, and no jumps. Formally, we say that f of c must be defined. This is the part that says no holes. Okay, f of c must be defined, meaning it has no holes. The limit as x approaches c, f of x must exist. That means that it has no breaks, okay? So in the first case, if you had a hole, I can't draw this graph without lifting my pencil, right? I have to put that hole there, yeah? That's the first case where the function doesn't exist. The second case is where the limit doesn't exist. Like that, right? That's a case where the limit doesn't exist. The third case, let's do this. The third case is where there's a jump, meaning the function exists because it has its filled-in value. The limit exists because the two sides meet, but the function value and the limit are not the same. So the third thing that could go wrong is that the limit and the function must be the same. So, whoops. The limit must be the same as the function. And this is no jumps. So if we think about these in terms of the picture of the graph, this guy, this guy means you can't have any holes. This guy means you can't have any breaks. And this guy means that these 2 points, the filled-in circle and the limit, must be the same, okay? If one of those three conditions fails at any point in your graph, then you say it's discontinuous there. So if condition number 1 fails, the function is not defined at x equals 3, you would say it's discontinuous at x equals 3. If there was a break at x equals -2, you would say it's discontinuous at x equals -2. If this third thing fails, the one with the limit existing, the function existing, but them not being the same, then you would say it's discontinuous at that x value. So here's a graph. And this graph says determine the points in the interval 0 to 5 at which the function has discontinuities. For each point, state the conditions in the checklist above that are violated. It could violate more than one condition, right? So we're going to look at every point between 0 and 5, and we're going to determine where we think it might be discontinuous. So what do you guys think? At x equals 1, discontinuous at x equals 1. Great. Because there's this vertical asymptote there. If I was trying to draw this graph, I definitely have to lift up my pencil at x equals 1 to get to the other side of that asymptote. Where else? 2. 2 has that big old break in it, right? 3 has a hole right there. Yep. And 4 seems okay, right? 4 is fine. I'm just traveling through 4. Everything's happy. There's no holes. There's no breaks. Yeah. So we don't care about 5 because we're only going from 0 to 5, right? So we're starting a little bit past 0, ending a little bit before 5. So 1, 2, and 3. So if we look at the checklist, and remember in the checklist, number 1 was the function didn't exist. If the function doesn't exist, condition 1 fails. If the limit doesn't exist, condition 2 fails. And if the function and the limit are not the same, condition 3 fails. So at x equals 1, which of those 3, 1, 2, or 3, or a combination of them, fails? Does the function exist? At x equals 1, does the function exist? No, there's an asymptote, right? So condition 1 fails. Does the limit exist? No, because it goes like to infinity, right? And then can they be the same if neither of those exist? No. If condition 1 or 2 fails, then condition 3 has to fail. So this is going to be it fails 1, 2, and 3. Okay, let's move to x equals 2. At x equals 2, does the function exist? Does the value of the function exist at x equals 2? Yeah, it has a built-in dot, right? So condition 1 holds. Does the limit exist at x equals 2? No, because it's broken. Okay, if the limit doesn't exist, then the function and the limit can't be the same, right? So 2 and 3 fail for this guy. Okay, here I am at x equals 3. Step number 1, does the function exist at x equals 3? No. Does the limit exist at x equals 3? Yeah, because the two sides meet. So this one's going to fail 1 and 3. Okay, so we're going to talk about 3 kinds of discontinuities, and they all relate to those 3 sort of properties of what it means to be continuous. And the 3 kinds of discontinuities are removable, infinite, and jump. Okay, so removable, infinite, and jump. Which of those 3 do you think are easiest to define? Jump. Okay, so what do you think a jump discontinuity is? It looks like what happens up there in the graph at x equals 2, right? So it has this big break in the graph. So a jump discontinuity happens when the limit doesn't exist, when the 2 sides don't meet, okay? Wow. That would fail condition number 2. The next one is asymptote. Which one do you think that is? Infinite, yeah. So an infinite discontinuity is going to be an asymptote. So if there's a vertical asymptote in your graph, you're going to call that an infinite discontinuity. There's no way for you to fix that. Okay, the last one is removable. Removable discontinuities are ones that look like what happened at x equals 3. So at x equals 3 in this previous graph, you can see that the limit exists, right? But there's a hole there, yeah? So removable discontinuities, you kind of think of them as holes in the graph. Not broken spots, not jumps, right? But holes in the graph. Basically, if you think about, can you fill in a number for that x value and make it continuous? So in this previous graph at x equals 3, if I had said y equals 1, I would have filled that in with a dot. It would have been a nice continuous line and everything would have been nice, right? So removables are places that fail, like the rule number 3, where the limit and the function are not the same. So fails 3, where the limit and the function exist, but are not the same. Okay, so a removable discontinuity fails number 3 up above, where the limit and the function both exist, but the two values are not the same. Basically, if you took away that value of the function and made it equal to the value of the limit, then the function would be continuous. So intuitively, when you're looking at a graph, you can kind of see where it's discontinuous, right? You're like, this looks broken, discontinuous. Then once you know where it's discontinuous, you should be able to identify which of these 3 types of discontinuity it has. So that's our goal. We're looking at a graph, we're determining where it's discontinuous, and we're identifying which kind of discontinuity it has. So take 2 minutes, look at these 3 graphs, determine at which value of X they're discontinuous and which kind, removable, jump, or infinite, of discontinuity it has. You can talk to your neighbor. Let me move them up higher.
Well, you only the first one to view.
And a graph may have more than one point of discontinuity.
No.
So first one.
This is the one's independent.
The first one.
So it's removable.
Remember, you're doing 2 things. You're telling me where the discontinuity is, and then you're labeling it which kind it is. Okay, we're going to start by just saying where they're discontinuous. Okay, so don't tell me what kind. Let's just say where they're discontinuous. In this first graph, where did you say it was discontinuous? X equals -1. This guy's discontinuous at X equals -1. How about in the second graph? X equals 2, that hole up there. And then the third graph? 0, and X equals 3. Okay, X equals 0, X equals 3. Okay, so now we're going to take each of these 4 places and we're going to label them removable, infinite, or jump, right? Removable, infinite, or jump. Are there any infinite discontinuities up there?
Yes.
Yeah, we look for the asymptotes. We look for the asymptotes. We see an asymptote in the third graph at X equals 3. That's an infinite discontinuity. Yes. Horizontal asymptotes. So horizontal asymptotes are Y values and discontinuities have to always be X values. So a horizontal asymptote would not give you a discontinuity. Yeah. Because this one has a horizontal asymptote, yeah, at Y equals 0. Okay, how about jump discontinuities? Do we have any jump discontinuities up there? The first one's a jump discontinuity, the place where that limit doesn't exist. Okay, the last 2 look exactly the same. Let me change the graph for a second. I'm going to change this graph and I'm going to put this dot right here. I changed graph number 3 and I put a dot right there. Does that change anybody's mind about what kind of discontinuity happens at x equals 0? If I put that dot there, does it change your mind about what kind of discontinuity happens at x equals 0? Turns out no. The only time a jump happens is when the limit doesn't exist. Okay? So the only time a jump discontinuity happens is when the limit doesn't exist. If I have a hole, whether it has a value or not, I can move that value and put it somewhere else. That's why it's called removable, because you can imagine moving the value of the function and putting it somewhere else. So even if it has the filled in dot somewhere, if the limit exists, it's a removable discontinuity. So these two at x equals 0 and x equals 2 are both removable. So removable is the one you think about, oh, I could fix that one. If I just took that dot and put it somewhere else, I could fix it and it would be no longer discontinuous. Okay, so if I have a graph of a function, it's easy for me to determine where it's discontinuous. Agreed? So if you have some equations of functions, how do you think you're going to determine where they're discontinuous? Yeah, maybe try to graph them, right? Sometimes the graph doesn't give us all the information. So we're going to try to graph them, and then we're going to say, do I have everything I need here? Okay, so sometimes you have to think a little bit harder than the graph because graphs are not very good at telling you all the information. Okay, so let's graph this function. I'm going to pull up Desmos, and I'm going to graph that function. You could also do the same or pull out your graphing calculator and you could put it in there. I can't get to my, I got it. I don't want to do it there. That's going to be bad. Whoa. Oh my God. It's a bad day. Okay, I pulled out Desmos. I got this picture. What would you say about this? It looks like there's an infinite discontinuity. It's really hard to tell what number that infinite discontinuity is at, right? Where do you think that infinite discontinuity comes from in terms of my equation? Where's that infinite discontinuity coming from in terms of my equation? Yeah, where the denominator is 0. That infinite discontinuity is coming from a place that the denominator was 0. If you remember what vertical asymptotes are, they're places where the denominator is 0. So that infinite discontinuity is coming when the denominator is 0. I think it's around -5. If we zoom in on the graph, I can see that it's around -5. It turns out, though, there's another discontinuity in here that you can't see from the graph, right? I mean, they're not good enough to draw you these, but watch. Here I am on these x values. I'm just moving along, moving along. Ugh, see it right there? At 2, it turned out to be undefined. There's a hole in this graph at 2 that you can't see. Yeah, that's tricky, right? So sometimes the graph is not the best way. It's one way to get a good start, but it's not the best way. How do I find the 2? How did I know it was at 2? Yeah, look for where the denominator is 0, right? So I have to find out where this denominator is 0. Okay, let's see if I can put this picture in our notes. Snipping tool is moving. Okay, great. I wish I could get rid of it. Okay, I'm gonna put that hole right there. Maybe I'm gonna try. There was a hole. Okay, so we knew that at x equals -5 and x equals 2, there were discontinuities. What kind of discontinuity is there at x equals -5? Infinite. It has a vertical asymptote there, yeah? How about at x equals 2? What kind are you going to call that one? Removable. Good job. Removable. Okay, I can find those places. If you can't find them from the graph, you find them by looking for places where the denominator equals 0. Solve this quadratic. Use your favorite method for solving quadratics, whatever it is. Factoring, quadratic formula, complete the square. I don't care what your favorite method is. At calculus point, you pick one, you make it your favorite. You don't have a favorite yet? Make it the quadratic equation. That should be your favorite. Okay, so you solve this, you get x equals -5, x equals 2. Whatever method you use to solve it. You can factor, you can use the quadratic formula, you can complete the square. Whatever method that is, right? That's a college algebra lesson. Okay. And then you know, you have to look at both of those places, -5 and 2 in the graph. Because places where the denominator is 0, you know funky things have to happen, right? That's when your light bulbs in your brain should be going off saying something weird's happening at these places where the denominator is 0.
And then people know that is there this funny place?
So then you'll know that those are the places you should look for in the graph. Yeah. Yep. There has to be a discontinuity there because the function can't be defined at those places. So it either has to be a hole or an asymptote.
Does the quadratic equation always work?
That's the only one that always works. Yeah.
Okay.
Factoring works like 0.1% of the time. Quadratic equation works 100% of the time. It might tell you that there's no solutions, right? It might tell you that your solutions are imaginary, but it will always work. Okay, here's another one. F of x equals square root 2x minus 3. What are you going to do for square root 2x minus 3? Yeah, do it. What are you going to do? You're going to graph it. Absolutely. We're going to graph that. We're going to graph it. Hooray, graphing. F of x equals square root 2x minus 3. There he is. What do you know about a square root? You put in any number you want. You can't put in any negatives, right? But once you have your domain, is it going to be discontinuous anywhere? It's going to be discontinuous when it makes this under the square root negative, right? But everywhere else, it's going to be continuous. When you draw a square root graph, you're not getting any holes or asymptotes or anything over there. So whatever this point is right here, 3/2. From 3/2 on, this guy is going to be continuous. So this guy is going to be continuous everywhere on his domain. There are not going to be any points of discontinuity. Snip him and put him in.
So for the last one, we have to get x and get waiting
Or which one?
for the last one.
The quadratic one?
No,
The square root one?
the last one.
Oh, I'm not there yet. I didn't even look at it yet. I don't even know what it is. Okay, so this guy's continuous. Continuous everywhere on the domain, which in this case is from 3/2 to infinity. Because that point right there is 3/2. So this guy's continuous everywhere. He has no jumps, he has no breaks, he has no holes, he's got nothing bad. Okay, let's talk about this guy. What kind of function is this? This is a piecewise function. Yeah, this is a piecewise function, and he has 3 pieces, right? He has one piece, this top piece, that gets used when the x values you're looking at are less than -1. He has another piece, this middle piece, that gets used when the x values you're looking at are between -1 and 2. And then he has one more piece, this bottom 2 to the x piece, that gets used when your x values are bigger than 2. Okay? If you consider these 3 pieces of the function separately, if you consider x squared minus 2x plus 1 by itself, do you think that's going to have any places where it's discontinuous? No, because there's no denominators, there's no square roots, nothing's going to go wrong with that guy, right? The x squared minus 2x plus 1 is going to be continuous everywhere. How about x plus 2? If you look at the graph of x plus 2, what's it look like? Straight line, right? Continuous everywhere, right? How about 2 to the x? If you look at the graph of 2 to the x, what does it look like? An exponential. It's like the swoopy one, right? Again, nice and continuous everywhere. So these 3 functions, these 3 pieces by themselves are continuous everywhere. Where might something go wrong? Yeah, where we switch, where they intersect, where they try to overlap, where we switch from one place to another. So in a piecewise function, if each piece is nice, meaning continuous everywhere, then the only problem spots are at the bounds, the switchings, the bounds, the switchover places. So in this case, x equals -1 and x equals 2 are the 2 places where we might have a problem, okay? Because when I use -1, I'm switching from the top function to the second function. When I use 2, I'm switching from the second function to the third function. So x equals -1 and x equals 2 are the places where we might have problems. Okay, to be continuous, 3 things have to happen. The function has to exist, the limit has to exist, and the value of the function. The limit has to equal the value of the function. The function has to exist, the limit has to exist, and the limit has to equal the value of the function. In a piecewise function, that middle thing, the limit existing, is where things might go wrong, right? When does a limit exist? If what? When does a limit not exist? Is that an easier question? If it's broken, meaning if the left side and the right side are not the same, right? The limit doesn't exist if the limit from the left and the limit from the right are not the same. Okay, so what I'm going to do is I'm going to look at these functions, this piecewise function. I'm going to compute the limit as x goes to -1 from the left and the limit as x goes to -1 from the right. I'm going to do the same thing at 2. I'm going to compute the limit as x goes to 2 from the left and the limit as x goes to 2 from the right. To do that, I have to decide. Here's -1. If I'm coming towards -1 from the left, I'm using the numbers that are smaller than -1. Agree? If I'm coming towards -1 from the left, I'm using the numbers that are smaller than -1. Which piece of the function do I use if I'm using the numbers that are smaller than -1? The first piece, the top piece, right? The top piece says use this if your x values are less than -1. So when I'm coming to -1 from the left, I'm going to use this function, x squared minus 2x plus 1. If I'm coming from if I'm coming to -1 from the right, my numbers are a little bit bigger than -1, right? Not a lot bigger than -1, just a little bit bigger than -1. So if I want to use numbers that are a little bit bigger than -1, which of these 3 pieces do I need? The second one. So when I'm coming from the right, I'm going to use the second function, x plus 2. Okay, remember to evaluate these, you just try to plug in the number, right? So what do you get when you plug -1 into this function? That's the first one. Four. What do you get when you plug -1 into the second function? What are you going to say? Yeah, discontinuous at -1. There's going to be a jump discontinuity there, right? The left and the right side don't meet. If I graph this function, and then on the left is going to be approaching 4, on the right is going to be approaching 1. Those two sides don't meet. Bad news. So discontinuous at -1. It has a jump discontinuity. Okay, I'm going to do the same thing again for 2. So I'm going to do the same thing again for x equals 2. Here's 2. First, I'm going to come towards 2 from the left. If I'm coming towards 2 from the left, I'm using numbers that are a little bit smaller than 2, like 1.9. If you're using numbers that are a little bit smaller than 2, which of these 3 pieces are you going to use? The middle one. Yeah, I'm going to use the middle piece because the 1.9 is in there between -1 and 2. So x plus 2. Okay, and then if I'm coming from the right, I'm going to use numbers that are a little bit bigger than 2, like 2.1. Using numbers that are a little bit bigger than 2, that's the third function, 2 to the x. Okay, then I just plug in 2. So 2 plus 2 makes 4. 2 to the 2 makes 4. Continuous at 2. So in this function, this picture here, the only place it's discontinuous is at x equals 2. Okay, let's put it in Desmos. I'm going to put it in Desmos by putting it in pieces. I'm going to say x less than -1. And I'm going to say my function is x squared minus 2x plus 1. Okay, I'm going to do the middle one. -1 less than or equal to x less than 2. And my function is x plus 2. Whoops. And then I'm going to do the last one. X greater than or equal to 2. Whoops. X greater than or equal to 2. And my function is 2 to the x, like that. Okay, there's my picture. Yeah. At -1, we have this big old jump, which is what we saw when we did those limits. At 2, the purple graph and the black graph touch each other, right? They meet right there. So nice and continuous. I mean, like it's a jagged line, but it's okay. I don't have to lift up my pencil to draw it. Okay, snip it. All I'm saying is Macs are far superior when you're taking screenshots. This snipper is just nonsense. Okay, I'm going to put it in down here. I'm going to try. It's not going to go where I want it to go. There we go. Okay. Let me drop this.